Okay, so good afternoon, everybody. My name is Christoph Vogl. I'm a now second-year graduate student at the Technical University of Munich, and I'm going to talk about a very experimental topic, which is xenon-doping of liquid argon for the legend experiment. But first, I need to introduce you to neutrinoless double beta decay, because this has not been discussed yet today, and this is what the legend experiment is searching for. Neutrinoless double beta decay is a nuclear process where two neutrons are decaying into two protons and two electrons, but without the balancing emission of neutrinos or antineutrinos. This means that it's a standard model violating process and has a change of lepton number by 2 units. This is very interesting, and the reason why we are looking for it. If we are able to detect it, besides the lepton number violation, we would also know that neutrinos are Majorana particles, which means that they are their own antiparticles, which would also shed light on the neutrino mass generation mechanism. You can look for this decay, where you can also look for the normal standard model allowed two neutrino double beta decay, which is in special isotopes, for example, Xenon-136 or germanium-76, which is what legend is doing, which is why I'm focusing on this. The two neutrino double beta decay has a continuous spectrum, as you can see here, and the no neutrino double beta decay would have a monoenergetic peak at the Q value of the decay. It has not been observed yet, but the strongest limits in germanium-76 have been provided by the Gerda experiment and are at the 10 to the 26 years level, which is much longer than the age of the universe, of course. So it's a very rare event. The legend experiment in its current phase, which is legend 200, is building upon the experience of the Gerda and Majorana demonstrator experiments. And it's looking for this decay in germanium-76 in high purity germanium detectors, where we employ about 200 kilograms in a large liquid argon truck stud, which has a volume of about 64 cubic meters. Liquid argon is used as a detector coolant, but also as a passive shield. Because argon is a scintillation, is a scintillator, any ionizing radiation passing through is creating scintillation light. Part of this liquid argon volume is instrumented with wavelength shifting and light guiding fibers, where silicon photomultipliers are connected to their ends. There are also other background suppression techniques or background suppression techniques necessary for an experiment like legend. So the signal looks like this. You have a double beta decay somewhere in one of your detectors. It's a single site event, strongly localized, and it's completely in the bulk of the detector. There is no argon scintillation light, no energy deposition outside. Backgrounds can be, for example, external gammas coming from Biospheric steel or wherever, and creating events in two different germanium detectors at the same time. We can get rid of these events easily by using a germanium anti-coincidence cut, for example. Then there is several energy depositions from external gammas in one detector, or alpha and gamma backgrounds, which are happening on the surface of the detectors. These events have special time distributions, which we can use to discriminate them with pulse check analysis. And then the third part of background is again external gammas, but they only interact once with one detector. So we cannot use the other cuts. We cannot use germanium anti-coincidence, and we cannot use pulse check discrimination. And this is where the active liquid argon shields comes into play, because gammas typically induce scintillation light when passing through liquid argon. And this we can measure and then veto the event. And this is the most relevant part for this talk, so I'm going to focus on this now. So liquid argon is a scintillator, as I said. This means that if ionizing radiation is passing through, something happens. Specifically, argon can get either ionized or excited. In the end, an excited argon molecule will be formed, which is not stable. It has two forms where it can occur. It can occur in the singlet state, which is super unstable and has a lifetime of about 5 to 10 nanoseconds. Or it can occur in a triplet state, where it's much longer lived, 1.3 to 1.6 microseconds. This excimer then decays and is emitting the 128 nanometers scintillation mode. The scintillation of liquid argon works well. Gerda has demonstrated it, legend is demonstrating it already now. but it's not perfect. It comes with some inconveniences. For example, the scintillation light has a very short wavelength of 128 nanometers, so it's very difficult to detect directly. Normally, it's shifted to a longer wavelength. Also, the scintillation time is pretty long, with more than 1 microsecond, and together with the high specific argon-39 activity in commercial atmospheric liquid argon, you get long signal time windows and also a significant detector gap time, always depending on the size of your detector. Also, the attenuation length is not huge. It's only 1 meter for pure liquid argon. And this, of course, limits your detector size. If you put a little bit of xenon into the liquid argon, so we're speaking about some parts per million, the picture changes drastically. Xenon can shift the scintillation wavelength to 175 nanometers, which can already be detected directly without the need for wavelength shifters. The scintillation time decreases a lot depending on xenon concentration, and also the attenuation length is increased a lot. And this is why it's so interesting to look at, also for the legend experiment, and why we are investigating this. So we investigate this by using a measurement device, which is a silicon photomultiplier array, and we submerge it into a liquid argon cryostat. This is a picture of the measurement device. It's called LAMA, which is the Legend Liquid Argon Monitoring Apparatus. It has 16 directly UV sensitive side PMs, which are here, and a scintillation light source at the bottom, which contains americium 241 emitting 60 keV gammas and then liquid argon scintillation light. And we use the source to trigger on the scintillation light, and then use the peripheral side PMs, which you can see here, to detect the scintillation light at different times and at different distances. So we can get the photo-electron yield from the source, which is the amount of light which is being produced, and we can get the effective triplet lifetime, so the scintillation time structure, and the attenuation length out of this device with only one measurement. We also measure the xenon concentration in the cryostat, both from the gas phase, which is at the top, and from the liquid phase from the bottom with a mass spectrometer, which is the impurity detector for investigation of xenon, or EGTIX for short. It has a sensitivity which is changing for different substances. So for helium, it's about 0.8 microliters per liter. And for oxygen, 0.5, and for nitrogen, it's a bit more, it's about 30. This is a picture of the mass spectrometer. It's wrapped in aluminum and it's connected to a turbomolecular pump. And on the left, you see some gas bottles which you need for calibration and background measurements. So the results of the scintillation run are shown in the plot on the right. This is a bit busy, so we need to go through this together. So you see on the x-axis there is time, and also the xenon concentration on the top. It should start with 0, which you cannot see because it's blocked, and then it goes to 3, 10, 50, 100, and 300 micrograms per gram xenon in liquid argon. And there are 3 different panels. In the first one, you see the amount of light, the photo-electron yield. In the second, the scintillation time, and in the third, the attenuation length. And we observed that the photo-electron yield is increasing as expected, because after the shifting, the photons are easier detected because of the higher photo detection efficiency for 175 nanometers photons. And the triplet lifetime is slowing down, and the attenuation length is increasing. There is a strange feature at 3 micrograms per gram, where the photo-electron yield is decreasing and the triplet lifetime increasing, which is counterintuitive and was not expected. But now we think it makes sense because the energy transfer mechanism of Xenon-doped liquid argon contains also a long-lived intermediate state, which could produce this, but we did not model it in detail, so I cannot say for certain. If we look in the stable phases, we get some more statistics, and we can say that the photo-electron yield of Xenon-doped liquid argon at 300 micrograms per gram, or ppm, so parts per million by mass, is doubling compared to pure liquid argon. the scintillation time is reduced by a factor of 10, so like 19 armor seconds scintillation time, and the attenuation length is very long, so more than 6 meters. This impacts legend in the following. So currently, the baseline design is still to use pure liquid argon scintillation. But the results look very promising, and it might be the case that we adopt xenon-doping of liquid argon soon for part of the Legend 1000 experiment, which is the next generation that is currently in planning. And if we do this, it is also a strong argument to then go a step back and say, we should also test it right now in our current setup, the Legend 200. So we might see it a little bit sooner than expected. To summarize, and here are just two pictures of the Legend 200 setup. The active background suppression in an experiment like Legend is super important, especially the active field with liquid argon scintillations of great use. Pure liquid argon scintillation is great, but it could be even better if we add some xenon. And we will, of course, pursue further R&D on this topic and might adopt it as a baseline soon. Thanks.
Yeah, so sorry that one of the slides was a bit blocked up there. So this, if I leave it, so this means that you so basically the different colors here are the different episodes with different target masses. Yeah. Or,
yes. Can you move it now?
Yeah, or you can even hide it. Yes. Hide. Okay. Yeah. Okay. Now perfect. So basically, at the start here, you increase. So it's not gradually; it's increase.
We inject xenon. We inject xenon at a certain time, and then you see it takes some time to mix.
Okay.
Into the argon cryostart. It doesn't go instantly. It takes some hours or a day, something like this.
Mm-hmm. Are there questions? So you had this device that somehow looked like a Christmas tree, which kind of has lost all its yeah,
yes,
all its things. Can you maybe say why do you exactly have this to I mean, what's the dimension of this? Is this going to be around the detector or inside the detector? Or?
So this is the monitoring apparatus. So at first, it has nothing to do with the germanium. It's just there also in Legend to monitor the liquid argon properties.
Mm-hmm.
The size is about a meter. So I think it's 85 centimeters tall from the bottom here to the top again.
Mm-hmm.
And the idea is to monitor the long-term properties of liquid argon in the experiment as it is right now. It will run for the next 5 years, let's say at least continuously, and observing if the scintillation properties change or not.
And this is submersed in the liquid phase?
Yes, this is in the liquid phase at the bottom of the cryostat. So it's a bit confusing because we have more than one cryostat. So this is the Legend cryostat, and here you can see all the llama is rendered there. So it's sitting.
There it is. Okay.
It's very small here. The germanium detectors are here. And llama is just at the bottom of the cryostat. And then we have a second one, which we have in Munich and use for R&D purposes. And this is what is shown in this picture. And this is our Munich cryostat. And there we do the xenon-doping, the R&D.
Okay. Thanks. Any other questions? Let's thank Christoph again.